Yeah, so this has been a really wild and crazy time, and I have to also apologize in case I forget how far things went. But there were like 2 or 3 reschedulings, and there was a bunch of running around with this because this fall was really crazy for us, and it's been a really wild ride for about a year longer than that. But among the things that happened a few weeks ago was this guy, my PhD advisor. And oh right, yes, that's right. We gotta rely on the old-fashioned thing here. This guy in the middle here, Kip Thorne, is he was my PhD advisor a while back, and he and a couple other guys got the Nobel Prize for last year's event. And I'll tell you about the first binary black hole detection, like it says in the title of the talk. That was the one that got the Nobel Prize, and then in the middle of August, just a few months ago, we got tied up with this other thing that made that one look boring. So this is actually from a couple of years back. This is me and Alessandro Corsi, who's another professor in the physics and astronomy department, and it was the first time he saw me with a Texas Tech name tag. So this was spring of 2015. I only came here a couple of years ago, and he was asking me, asking us both, how do you guys like it out there? And we were saying, yeah, it looks pretty cool. And of course, so apparently Alfred Nobel's will has this stipulation that no more than 3 people can get awarded for something, but as I predicted long ago, Kip was the first to point out that this is really the work of, it's on the order of 1,000 plus a little bit more people. There's this thing called the LIGO Scientific Collaboration that we're all part of, and this has, it's currently, actually this slide's a little bit out of date, it's grown since then. The LIGO and the European Virgo project working together, even if you just look at the LIGO Scientific Collaboration, there's something like 60 universities and research institutes, and there we are, and there's other, like there's UT Rio Grande Valley, there's other places all around Texas, there's Caltech, California, that's where Kip is, that's always been one of the big players. And then there's Penn State where I used to be. There's and then there's Cardiff and Wales. There's Australian National University. There's I forget what this alphabet soup stands for, but these are the Brazilians. There's all kinds of people involved in this. This is a really big effort to build these beasts and then analyze the data and figure out what's going on in the far reaches of the universe from that. But to go back to the very start of it, the idea is very simple. Okay, getting here involves the Einstein field equations for gravity and a lot of complicated stuff, but if you just take this as your starting point, a simple starting point, the gravitational waves exist and they look like this, then you can go a long way with filling in a lot of other things with just some simple fill in the blanks. And the idea here is that this is what it looks like if you have a gravitational wave that's traveling straight out of the screen or straight into the screen. So all the activity is in this plane perpendicular to the normal, perpendicular to the direction of travel. And many of you will probably know, like, that's how electromagnetic waves work too, in your basic science and engineering classes. And the idea here is that you have, you start off with some circle with a bunch of beads arranged on it, and this demonstrates what's going on. This animation tells you what's going on as the gravitational wave propagates out of the screen, say, then as it goes by, what you get is alternately, in one dimension you get the thing that starts as a nice circle before the gravitational waves come through. You get it squeezed in one direction and stretched in the other, and as the wave propagates out a half cycle, it goes the opposite way, squeezed in that direction, stretched in that, and it keeps doing that. That's basically what a gravitational traveling wave looks like. And let's see, in physics we actually usually don't tell people about this until they're pretty advanced. It's usually engineers who do a better job of mentioning this even at the freshman level. This type of motion where it's squeezing and stretching in different directions is called a shear. And it's fundamentally it's kind of the same thing like ripping up a piece of paper. And here, so the strain is the dimensionless amplitude of this, like how far is one of these red dots moving as a fraction of how far it is from, how far is the diameter of the circle. So it's a dimensionless, length perturbation over the total length. And while I've been talking, you could probably eyeball this and say, well, okay, it's a bit less than 10 ticks wide, and it's moving on the order of a tick, so the shear strain is something on the order of 1 in 10 to the nearest order of magnitude. But, and this is a slide that I've been using for many, many years. In real life, we were saying, on a really, really good day, the shear strain, this is exactly the pattern that you're looking for, but on a really good day, the amplitude of this, instead of 1 in 10, is going to be less than 1 in 10, well, this is 21 zeros, maybe you've had time to count them by now. So in real life, you're looking at a strain amplitude on the order of 10 to the minus 21, which is very, very hard to measure. And yet, it's been done. LIGO, the acronym, like you heard before, is Laser Interferometer Gravitational Wave Observatory. The basic idea of LIGO is that you take advantage of the fact that you're getting squeezed in one direction and stretched in the perpendicular direction to basically fill an L with laser light. You shine a laser in, there's a beam splitter, and so half of the beam goes off this way, half of the beam goes off that way. It bounces off of the mirrors and comes back and gets recombined in phase or out of phase, and that determines what you see at the output. And many of you will have done, this is a laser interferometer. It's a precision tool for measuring very tiny length changes. And many of you will have played around with these in your freshman or sophomore labs in a lot of physics or engineering courses, right? And I see a lot of people, a lot of you have played around with this. And you know what a pain in the ass those are, because they're so sensitive, right? You breathe on them or bump something, you're trying to lock on a certain fringe, and it's incredibly sensitive what a tiny bit of length change these things are responsive to. Well, that's actually an advantage here. We're trying to get it to respond, and it's just like the kind of thing that you played with in your lab class, except these arms are 4 kilometers long for LIGO, so 2.5 miles long. These are pretty big installations that you drive around to deal with stuff. And, well, okay, real LIGO is more complicated. There's some other stuff you'll see in here, like there's a power recycling mirror and a signal recycling mirror and a bunch of other games that get played with coupling other resonant cavities in there. But the gist of it is very simple. Just like that tabletop interferometer many of you have played with, you're looking for differences in length between this arm and this arm show up as signals in the output. And this is where that strain number of 10 to the minus 21 comes in. If you say, okay, 10 to the minus 21 is the fractional length change, and you plug in 4 kilometers for the actual length, then that tells you you're looking for a signal on the order of an absolute length change on the order of a few times 10 to the minus 18 meters, which is less than a thousandth the thickness of a proton, for example, which is 10 to the minus 15 meters. And an atom is on the order of 10 to the minus 10 meters. And for that matter, the wavelength of the light, which makes it so annoying when you bump the table in your freshman lab or whatever and you lose lock, the wavelength of the light here is a micrometer. It's 10 to the minus 6 meters. And you may certainly those of you who went through this pain with the lab class went through this bit about how you're picking up a fraction of a wavelength of light changes in your length, and that's on the order of 10 to the minus 6 meters, and how do you get down to 10 to the minus 18 meters? And well, a large part of the answer comes from the fact that you're averaging over a lot of atoms. So these test masses with mirrors on them, these test masses that are hanging freely so the gravitational wave can move them around, and the mirrors on each side let the light bounce back, those are big blocks of stuff, right? They're on the order of something like 20 centimeters across, and you're looking at what an Avogadro's number. A mole is of order 10 to the 24 atoms, and so you're shining on one face of this cube, so you're averaging the displacement. The laser beam has a spot that's about that big, so you're averaging over. Going from a cube to a square to get the area, looking at the top layer of atoms, you're averaging over something like 10 to the 16 atoms, and that's Poisson noise, so the error goes down by 10 to the 8, so that takes you down from 10 to the minus 6 meters to 10 to the minus 14 meter sensitivity. And then there's another factor of close to 1,000 that you gain from what's called the finesse of the cavities, which is the fact that, you know, when you have these mirrors, there's a mirror here and a mirror there, and the light bounces back and forth many times. On the average, that number is something like 400 or 500. It's close to 1,000. So now you're down from 10 to the minus 14 meters to 10 to the minus 17 meters. You know, you've built up your signal with the extra bounces. And then the remaining order of magnitude is there's a couple things like, you know, you're not just looking at the top layer of atoms on the test mass, you know, it penetrates a bit more, and obviously if I'm just talking powers of 10, this is a very sloppy thing, and you know, and when you put in factors of square root of 2 and pi and stuff to do it properly, it gets a little better. So that's basically where the 10 to the minus 18 meters comes from. It sounds crazy, but it's real. And I had, you know, I used to have to go through all that rigmarole to convince people. And well, let's see, before I move on, let me say, part of the deal is that, yeah, just like, you know, every time you breathe or bump that thing in your freshman lab, the interferometer gets the jitters and goes all over the place. Yeah, obviously with 4-kilometer arms, there's a lot of opportunities for that. So there's a lot of seismic isolation. There's a lot of stuff going on to make this really clean and stable. But even then, you really don't want to trust just one of them. And so there's these two facilities called H1 and L1 for the primary Hanford, Washington interferometer and the primary Livingston, Louisiana interferometer. And there's a 3,000 kilometer gap, which is about 10 milliseconds light travel time between them. And that's important to get confidence, first of all, to get confidence that you've seen something when both sites show the same sort of signal. And you know, and there's things like, you know, the Hanford Nuclear Reservation reactor cores being driven by these giant caterpillar sort of things that shake the ground, and that doesn't happen in Livingston. And then there's something called a PIG, which is a metal plug in an underground oil pipeline that goes a little uncomfortably close to Livingston, and you know, they don't have that at Hanford. So you know, you get different things happening, different spurious disturbances, and you got more confidence. And it turns out having two locations lets you figure out where on the sky the signal is coming from a bit better. Let's see. The last bit of this plot is, well, this is in funny units. Strain is dimensionless. This is strain noise per root hertz. If you know what a power spectral density is, like the electrical engineering types maybe know that. That's what that is. And if you don't know about it, you know, don't worry. This is, you know, it's slightly off because of the, you know, the funny thing you have to do when converting strains into noise. But you can kind of tell the noise is at its best, noise is at its lowest, frequencies of a few hundred hertz. So that's in sort of the audio range for the human ear. And like I was saying, you know, I used to have to go through this whole thing to convince people that 10 to the minus 21 was possible, but that was actually what we observed right when we got going in September of 2015. And we didn't actually publish it and let it out until February. Yeah, there we go. 11th of February of last year. There was this big hoopla. This is the cover of the journal. On top is, you know, this is sort of a cartoon version of binary black holes spiraling together and merging. And then on the bottom, this is the signal that we actually saw, the signal in each interferometer. Although for some reason the reddish orange one isn't coming out too clearly on the screen. Maybe it's the same reason it eats this red laser. Anyway, you know, the basic idea here is that, you know, for a long time people have predicted that, you know, double black hole or neutron star systems, you know, this is something that's obviously a very relativistic system, but you can go a long way to a decent approximation just using Newtonian mechanics and talk about like Kepler's law for orbits. You know, those of you who've been through freshman physics will know that, you know, you know, square of the orbital frequency times the cube of the orbital radius is a constant, and that works pretty well even when you get into issues like with curved space-time. Defining the radius in a good way is, well, actually you can't, not in a fully good way. But if you just use Newtonian orbits, you know, Keplerian orbits, and just stick in the additional bit that there are gravitational waves taking energy out at a certain rate, depending on the frequency of the orbit, you can get a remarkably accurate, you know, you can come up with a gravitational wave strain as a function of time, which looks an awful lot like that. which is what we saw, except that the jagged bits on top of it are noise in the detector. That's always present and something you have to worry about. So here's a slightly better version separated out, well, several separated versions. So here's the signal seen at Hanford, Washington. Here's the signal at Livingston, Louisiana, and the strain units are 10 to the minus 21. So that's about what we were able to see. There's been some filtering on this signal to get rid of the very low and very high frequencies where the noise dominates. So this has been whitened. That's when you try and get rid of the fact that the noise grows at low and high frequencies. But otherwise, this is pretty raw. So you can see there's a signal in there with some jagged stuff on it. And this is, the Livingston one is shifted by 7 milliseconds, which turned out to be important for trying to figure out where it comes from. Because remember, there's a 10 millisecond delay if you go straight from one site to the other. So if a signal is coming right along the line from one site to the other, that's a 10-second delay. And then the fact that it was 10 millisecond, and the fact that it was 7 milliseconds tells you it was somewhere on this cone, which is about a 45-degree angle to the line of sight between the two. And so this is the actual data. This middle bit here is a reconstruction, various reconstructions of the theoretical waveforms that were predicted, and you can see, they match really well. There's a bit of junk on top from the detector noise, but you can see pretty clearly, there's something on the order of 10 cycles growing, and the idea is that, as the orbital energy decreases, even in the Newtonian picture, it's fairly accurate. As the energy decreases, the things spiral together. They're gaining kinetic energy. They spin faster and faster, but they lose potential energy as they get closer and closer together. So the amplitude and the frequency both go up, and then bang, they hit each other, and there's a little bit of a ring down, which you could even kind of see in the data. There's the final black hole that they make by merging together is a bigger black hole, and that's highly disturbed, so it rings down like a bell for a few milliseconds. And the whole thing is over in a couple hundred milliseconds tops. And by the way, that duration is highly tied to the mass. That's a very good way of reading off the total mass of this thing and saying that it was on the order of 60 solar masses. Down here, well, let's see, here noise residuals, like if you subtract off the putative signal, what you get is consistent with pretty much Gaussian noise. And then here is something called a spectrogram, which again, probably the electrical engineers are more likely than most of the scientists to have seen. This is basically, the colors represent sort of a power, signal to noise ratio per unit, or I forget if it's per unit time or cycle, something like that. But it's basically, frequency versus time. There's this track here which tells you there's something at low frequency lasting, on the order of 100 milliseconds, and then it's getting higher and higher and louder as the color intensifies. And if you actually play it on audio, which I tried a couple of times and I don't anymore because it doesn't really do it justice unless you have like rock concert quality speakers. But you can go to www.ligo.org, and if you have good headphones, you can listen to the sound files there. Anyway, it sort of goes whoop, and it makes this little chirp, and it is audible. It's in the human frequency range, although the amplitude's really tiny. So let's see. Let me move on a little bit quicker here. Yeah, basically from the total duration of that, just from the Kepler's laws and the orbital mechanics, you can work out to a really good approximation what the total mass of that thing was, and you can actually let me go back a little bit and explain a little bit more. You can actually, in this part of the signal, from the chirp rate, you can tell what the two masses of the individual black holes were, and they add up to 65 solar masses. And then from this ringing down bit at the end, you can read off what the mass of the final black hole was, and that wasn't 65 anymore, that was 62. So that tells you 3 over 65, about 5% of the mass energy was radiated in gravitational waves, which made it exceed by a little bit for that few hundred milliseconds there at the end, it exceeded the total luminosity of every star in the universe in a completely invisible form. So that was pretty impressive. So anyway, that was just the first one. That was detected in September of 2015, and so these things are named by the calendar. GW 150914 says September 14th, 2015, and you can see the individual masses were, I think, 29 and 36. That should have added up to 65, but at the end it had added up to 62. And then there's a bunch of others we've detected since then, going all the way up to August 14th of this year. That remains the most massive one. And then there was the one, actually this is the second to last one we detected, but it's the most recent one we published just a week or two back. This is the lightest one, where there's a 5, like a 6 and a 12 making a 17, something like that. Again, there's a deficit of on the order of 5%. That's an incredible amount of E equals mc squared that's been radiated away. This one is in dashes because these others were incredibly loud, and that one was, loud enough that if this was a mature field, like sort of existing branches of astronomy, we probably would have called that a detection. But we've been very picky so far. I mean, honestly, that thing probably was real. It was loud enough, but we've been using a ridiculously loud threshold to qualify these things. So you had a question.
Is that would that be why the letter notation for?
Yeah. So instead of GW, it's called LVT for LIGO Virgo transient. And yeah, there's a long story there about how this thing happened right when we turned it on, and it was incredibly loud and incredibly massive, and rewrote. People didn't realize that there would be black holes this massive. I mean, they're the ones that you see you see the traces of in X-ray binaries previously are down around 5 to 10 solar masses, and then there are things that live in the centers of galaxies up at millions of solar masses, like our galaxy has a couple million. But there was nothing, up at 30, 60, something like that. And so that was kind of a surprise that gave people some insights into, the lives of massive stars. And now there are thoughts that maybe, small galaxies form from lots and lots of mergers of these. It's kind of hard to tell yet. But as we collect more of these, we're going to get good demographics and get some idea what's going on. But there's a long story there that I'm skipping over because all of this, including the questions, is in 1 hour, right? So, aiming for 45 or 50 minutes. Yeah, so I'll just say there's a lot of stuff going on with the black holes, and the Nobel Committee made that like the fastest prize in history. But from the beginning, those of us at Texas Tech have been saying that, okay, yeah, neutron stars, yeah, the black holes are all fine and well, and it was a big surprise actually that we detected those first. We were thinking we would detect binary neutron stars first, and we, all along, those of us at Texas Tech had been more interested in neutron stars because there's a lot more complicated stuff going on. Black holes are just holes. There's nothing there. What you're sort of seeing, what you're measuring the effects of, is the effects of event horizons, which are just, sort of tears that are left behind when all that, the mass of the original star is collapsed away out of the bit of the universe we can see. But neutron stars have matter, which is all sorts of complicated, messy stuff. But it's, roughly speaking, there's a couple of ways you could view a neutron star. One way is you could say, okay, it's an atomic nucleus, an atomic nucleus with not an atomic number on the order of a couple hundred, like the most massive ones we see on Earth, but on the order of 10 to the 50 something. Another way you could look at it is, okay, a blob of condensed matter, so two areas of physics, nuclear physics and condensed matter. You could say, well, this is a blob of extremely condensed matter. It's on the order of 10, 12 kilometers radius, so the whole thing would about fit within the loop that goes around Lubbock, the 289 road. But this stuff is compressed. This is the remnant you get when a certain type of star collapses down. There's a supernova explosion. It blows off its outer layers in this spectacular explosion, and then there's a remnant left, something on the order of 1 to 2 times the mass of the sun, that collapses down, and it can't get held up by the heat from nuclear reactions anymore, because the nuclear reactions have run as far as they can go, and you get this blob of stuff collapsing down further and further until it's an average density. If you pack a solar mass into a 10-kilometer radius, you can work out the average density is a bit more than the density of an atomic nucleus. So the average is a few times 10 to the 14 grams per cubic centimeter, where water is 1 gram per cubic centimeter. rock, iron is like 7, rock is like 5. So that this is amazingly dense stuff. And in the center, it can go above 10 to the 15 grams per cubic centimeter. So we know pretty well what happens, when you crush stuff down under those conditions, is that the protons and electrons in normal matter get sort of crushed together to form neutrons. That's why it's called a neutron star. And we know from nuclear physics that at nuclear densities, sort of in these intermediate regions, you get these liquid drop atomic nuclei where we sort of we understand a lot of how they work. But when you get to really high density in the core, then even the neutrons and the few remaining protons and electrons might give way, and you might get funny particles. There's a lot of particle physicists who have made careers for 50-odd years talking about there could be hyperons, meson condensates, quarks. There's all kinds of funny stuff that can happen if you go ask them. There's all sorts of weird stuff going on with this matter. It's under such extreme conditions that it's hard to it's hard to compare to stuff we know. But you can actually work out a lot from extrapolating from various nuclear physics and condensed matter experiments. And then there's some astronomical observations. Like we know out of this 10-kilometer radius, roughly the last kilometer or so has to be more or less a solid because of behavior that we see in radio signals from spinning neutron stars, which there are a few thousand known in the galaxy, and there should be a lot more that we don't see. There's all kinds of properties you can work out too if you work out basic numbers that control everything, like the Fermi energy. That's one that many of the physicists or the materials scientists or chemists will have heard of. And the Fermi energy for these things is on the order of hundreds of mega electron volts, whereas it's typically like a few electron volts at most for stuff that you're playing around with in the lab. Like for metals, it's on the order of like 10 electron volts. So this is off the scale. It's millions, tens of millions times higher Fermi energy, and you get a lot of weird behavior. Like even at temperatures of 100 million degrees, which we see because some of these things have thermonuclear fusion of infalling matter on the surface. We can see the X-rays. Even at those temperatures, the material is essentially zero temperature compared to the Fermi energy, and you can work out that fairly quickly this stuff ought to form even at 100 million degrees. That's absolute zero as far as the Fermi energy is concerned, and it ought to be a superconducting superfluid. Superconducting because there's still a little bit of protons and electrons around, and superfluid, and you've probably seen demos of superfluids crawling up the walls of containers and having zero viscosity and all that sort of thing, and yet the weird composition of this means that when it goes to a superfluid, that actually dramatically increases the viscosity over the young days of the neutron star when it's hot. Anyway, there's all kinds of stuff I could say again, which I ought to move on from and get back to LIGO stuff, but I always like to mention that I don't think I've ever written one paper on neutron stars that's gone through volume 1 through volume 10 of the Landau-Lifshitz series on theoretical physics. I think I was actually trying to count this up, and I think the record was like 6, touching on 6 of those topics in one paper. But over the course of multiple papers, it's easy to go through all 10. There's all kinds of stuff going from basic mechanics to classical field theory. Relativity is an important thing in neutron stars, as you can work out when you calculate the gravitational redshift of something that mass, that radius. There's superconductivity, superfluidity, there's quantum mechanics, there's all this stuff going all the way to volume 10, physical kinetics, which is it's kind of an old-fashioned term, meaning when you calculate scattering cross-sections of neutrons off each other and turn that into a coefficient of viscosity like you would run into in fluid mechanics, or elasticity properties, I've calculated the shear modulus and people have calculated the breaking strain of this stuff. So anyway, this is a lot more than a simple black hole. There's a lot of complicated stuff that can go on here, including gigantic magnetic fields and other stuff. But you had a question.
I do, yeah. So free neutrons have a half-life of 1,000 seconds or so?
Yeah.
But they're stable in a nucleus.
Yeah.
Are they stable in a neutron star?
They're stable in a neutron star because the compression shoots the Fermi energy up. So, the Pauli exclusion principle blocks, if you want a neutron to decay, you need to make a proton and an electron. and those states aren't available until a much higher energy.
Gotcha.
So yeah, so they're stable. Anyway, yeah, getting back to LIGO. So yeah, we saw, what was it, like half a dozen of these binary black holes, depending on how you count them. You know, do we count that second one as real or not? But then just a few days after the most recent one of them, that was August 14th. This is the August 17th event. Here is something that is a time frequency plot, you know, so that speckling is noise, and here again you see this trace of a chirp. And by the way, it's really amazing that you can see this by eye. You know, we actually use sophisticated signal processing techniques to pick this out, like matched filtering is the basis for the most sensitive ones. That was developed for radar during World War II, and then of course, you know, it wasn't actually published until years later. They were keeping a lid on it, but you know, it's the same thing that submarines use for sonar today, and you know, it's just you can actually prove it as a mathematical theorem. That's the best you can do. But even without that, just by eyeballing it, you can see this about 30 seconds long track in the speckling from the noise. This is, you know, frequency versus time, and then the color indicating power again. And this is the one that you really want to have good bass on your speakers or really good headphones, because there's this rumbling, and then it just chirps up at the end, and you lose it in, you know, the high frequency noise, which has been normalized out. But the bit that you can see by eye is 30 seconds long, which is amazing. And then if you actually use the more sophisticated signal processing, it's you know, 2 or 3 minutes long, basically. There's significant signal to noise that you can pick up for going back about 2 or 3 minutes. And this right away tells you, you know, basically from Keplerian type orbital mechanics, this tells you that the total mass wasn't 60-something solar masses, it was 2.8. So the longer signal evolving more slowly tells you it's 2.8 solar masses. And that's a very significant number. It turns out, so that's very significant for talking about this as a double neutron star. Now, I would just say, you know, the 2.8 right away is very fishy. The 2.8 is measured very accurately, basically from the length and the chirp rate of the signal, and you know, almost Newtonian orbital dynamics. There's a little correction, but it's pretty good. And 2.8 is very suspicious because for decades that's what people found when they would find these double neutron star systems in radio. There's something like a couple dozen of these things known now where you see 2 neutron stars spiraling around, and you know, within a few 100 million years they'll get to the point where they crash and do that thing where we see the last 30 seconds or couple minutes or so. So that, you know, they're not going to go anytime soon, but that's how we estimated population statistics and so on. And those were all total solar mass, almost exactly total mass almost exactly 2.8 solar masses. And that was very fishy. A lot of people for a long time believed that neutron stars had to be 1.4 solar masses. Nowadays, we know that they can be about from 1 to 2, and there was a selection effect that these double neutron star systems, because of the way the time scales and the interactions they had to have to evolve like that, it heavily selected for things that were almost 1.4 solar masses each, for a total of 2.8. So the meaning of this plot that you've been puzzling at while I've been talking is, if you try and separate out the two masses, there are these highly correlated errors. Getting the total, the total is if you go along this axis, you know, this is M1 versus M2, this banana, which is your 90% error region, is very thin in that direction, so you can get the total mass pretty precisely. But if there's highly correlated errors, if you try and read off, you know, M1 minus M2 the other direction, this thing is very, very long. So technically, you know, there's some probability that these things could be above 2 solar masses, which is about where a neutron star would collapse into a black hole. So just based on the masses, technically you couldn't quite claim that it was a binary neutron star detection, although the total, again, was very fishy considering what people had seen in radio. There's other reasons it's a neutron star, but I'll get to that in a moment. I thought I ought to mention really quickly, even though there wasn't a result here, this is a non-detection and therefore an upper limit. This is actually a really cool thing for neutron star physics, and it's actually the main thing that I was working on the first half of this semester, so I thought I'd talk about that. This is a similar thing where instead of mass 1 versus mass 2, you're looking at these tidal deformability parameters. So for neutron stars, one of the things that happens is, that as they get closer together, they raise tides on each other. They raise these bumps on each other from the gravitational field varying over the dimensions of the star. Just like with the Earth and the Moon, you get tides. And with the Earth, the tide is, there's basically this big blob of water that's sort of distended in more or less in the direction of the Moon. And that actually grabs on to the Moon. It changes the gravitational field in a way that slightly alters the Moon's orbit, and the Moon has actually been spiraling out for many millions of years, by the way. There's a similar thing going on here that, it affects that Newtonian mechanics at 2-point masses. It changes the chirp rate slightly, and you can read off basically the tidal lumps on each neutron star. And there's so these lambda 1 and lambda 2 parameters are basically bang for the buck parameters. Like, how much does it respond? Like the Earth, there's this big blob of water that comes around twice a day, from the Moon. The tidal effects also hit the rock, but the rock only moves a little tiny bit. You don't even notice it normally. So there, depending what it's made of, there's different responses, and whether this stuff is soft or stiff, which could tell us a lot about nuclear physics and particle physics. And so the color here represents a probability density, and this is roughly the 90% level. Basically our results are consistent with zero tidal deformability, and this is the 90% confidence upper limit. So we're basically ruling out these gray bananas, or what you would expect from a neutron star if it had various equations of state that the nuclear physicists have postulated. So we've ruled out a couple of things already, just from saying that like these equations of state, the star would be really stiff matter that would then result in the star resisting gravity a lot and being bigger than if it was made out of squishy stuff. And if it's bigger, then the tidal effect is how the gravitational field changes across the dimensions of the star, and so it's got more of a strong coupling to that. So the fact that we didn't see that happening has already ruled out a couple of things, and we're even doing a better reanalysis. And okay, I should really keep moving here. There's a few more funky things to look at. I mentioned the benefit of having 2 detectors. Well, one of the ways we got fantastically lucky with this thing was that we got a 3rd detector, the Virgo detector in Europe, where Professor Corsi actually started off working as a postdoc. That one's over in Italy, and the thing is that I mentioned that when when they had that 2, just the Hanford and Livingston, Virgo wasn't on for the binary black hole one. When you had just those 2, and the light travel time wasn't 10 milliseconds, it was 7, that told you it was somewhere on this cone, so it would make this big ring on the sky where you could say it could come from like this. The ring would get narrowed down a little bit by their beam patterns. The amplitude of the signal depends on where you are. It's not just a matter of timing and trigonometry, although that gets you a good rough approximation at first. But when you get 3 detectors going on, you can localize it a lot better down to this little ellipse on the order of 20-something square degrees. And that was even though Virgo didn't see it. So basically, when in that first slide, when I talked about how there's this stretching and squeezing, going on, one in one direction, one in the other, something that may not have occurred to you right away is that if you have a signal coming in from the plane of the detector coming in like this, then there's no signal, because the arms there's no differential signal in the length of the arms. They're doing the same thing. So there are these 4 blind spots in the plane of the detector at these angles. And so the fact that Virgo didn't see anything was actually really useful. It nailed it down to one of these blind spots and got us an error region small enough that we could figure out where, based on the fact that this was likely a neutron star, we could tell our partner telescopes where to point, and we could get a pretty decent reading on the distance, which is around 40 megaparsecs, 130 million light years, which is very, very close as these things go. That distance reading, when we found the electromagnetic counterpart to this thing, we were able to, with optical telescopes, to track it down to a certain galaxy and measure the redshift of that galaxy. And so when you relate the distance to the redshift, that's related to something called the Hubble Constant, which tells you about the expansion of the universe. And we were able to do a measurement that, so that there's a long story here, which I'll mostly skip over, except to say that there's generations of these 2 methods producing different results. here's the Hubble constant in certain units down here, and here's the yellow band is the high one, which is around 73. The 68, 69 is the blue one. That's from the Planck satellite. And then this curve up here is our probability density. So it's lopsided, so we're not just quoting error bars. And you can see that our error is too big to resolve the discrepancy between the two, which has been narrowing down and people have been arguing about for generations. But this is just one measurement, and we'll get more. And a really cool thing about this measurement is that the reason these people have been fighting for 50 years over this isn't just big egos, although there's a long story of those too. But they do all these complicated things, like there's this whole chain of working out the cosmological distance scale, from going from parallax measurements of nearby stars to population statistics of the colors and how the colors relate to the luminosity and the temperature. And then there are certain variable stars that seem to pulse in a certain time depending on their luminosity. And there's this huge long chain of inference to get distances to galaxies further out in the universe, which is obviously subject to all sorts of systematic errors from various assumptions not quite working out. Like what if some of these stars pulse a little differently? And with us, it's just a raw measurement. There isn't any of that. So this is really promising for the future. And then of course, the real kicker for being a binary neutron star was that there was a gamma ray burst right afterward. So here's the LIGO signal, and then whoop, it ends, the two neutron stars merge, and 1.7 seconds later, this is a light curve, a count of gamma ray photons per second in one of the satellites. There was a bunch of satellites, I just picked one. There was a bunch of them that observed a gamma ray burst, a flash of gamma rays coming from outer space, 1.7 seconds after the LIGO event, which tells you, this was a binary neutron star, not binary black holes, which wouldn't be expected to produce anything. But there's matter here. The idea is that when the two things merge, there's sort of this fireball of stuff, and then probably because of interaction between the magnetic field and the spins, there's a blast of material that gets collimated in these jets going out at the poles. And it takes a second or two to plow its way through all the cloud of gunk and come out, and that's entirely consistent with what they saw. And there's all sorts of cool stuff you can do with this, like putting a limit on, in general relativity, if that's the right theory of gravity, gravitational waves ought to propagate at c, the speed of light, and you can look for deviations from that, and people had done that before through various experiments, and this delay, like even if you forget about the fact that this is consistent with the time to plow through the fireball, if you say, well, what if this is all due to some discrepancy in the speed of gravitational waves versus the speed of light, at that distance it works out to a bound 1,000,000 times more strict. It's like 10 to the minus 15 now, fractional bound on the difference between propagation speeds. And there's all kinds of stuff. And so the gamma ray flash was right away, and then within about 11 hours, a bunch of optical telescopes, thanks to the gamma ray flash didn't aim very well, but LIGO and Virgo, with Virgo not seeing it, were able to aim at a small enough patch of sky that these telescopes, including former Professor Dave Sand, who was here, he was here until a couple of weeks before this happened. He just moved over to Arizona. He and a bunch of other people had these telescopes set to look very fast for these transients, and they caught this little dot rising in this next to this obscure galaxy that wasn't there before over the space, this 10 or 11 hours, and then people kept observing. This is an X-ray satellite that first saw the dot. There's the nucleus of the galaxy. There's the new source after 9 days, and then the Very Large Array over in New Mexico, over near Socorro, New Mexico, saw that, and that was our Alessandra Corsi, our own Alessandra Corsi, talking about it at the press conference a few weeks ago in DC at the National Press Club. She was the leader of these radio observations that detected this thing. So there's all kinds of information they're getting out of that, and people are talking about, well, maybe the most publicity friendly one is people talk about 10 times the mass of the Earth in gold made in that, because this is actually a big channel for how the heavy elements form. So I mentioned when neutron stars are formed, the light elements are formed by nuclear reactions in the cores of stars, like our sun is burning hydrogen and producing helium in the core at the moment. And as it nears its death, it'll go through several cycles going up to something like silicon. But then even with a bigger star, you can go through a few more elements, but then iron, atomic number, mass number 56, atomic number 26, once you go up to there, the nuclear reactions stop, and you can't make heavier stuff like gold and various other things in the nuclei of stars. So people had speculated for a long time that this was going on, and basically by looking at the electromagnetic stuff, the electromagnetic signals out of this, the radio, the optical, and so on, people were able to work out that 10 Earth masses of gold and another 10 Earth masses of platinum were made in this explosion, and that's a very significant source of the heavier elements, which then gradually the stuff blows out and goes through the galaxy, and little bits of it end up in us. I mean, people keep going on about the gold mine, but there's all sorts of stuff about things in your body won't work without there's all sorts of these heavier elements that are needed for bits and pieces of your nervous system functioning or energy transport in the blood and various other things. So that's actually far more important than pouring old gold. But anyway, I skipped over a lot. We're approaching the 50-minute mark. So let me just say there's an awful lot more there. And again, good bits of it that you can understand with fairly simple things like doing a Kepler's law level calculation, just with a tiny bit of stuff stuck in, the gravitational waves stuck in. This is just the beginning. So LIGO went down, Virgo went down a few days after that. That was another way we got lucky with that event, the binary neutron star event. But there's a planned series of upgrades over the next few years. So these are noise curves again, noise versus frequency. And the upgrades are going to, the noise level is going to go down, 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 and then we ought to hit, a really long run at the full design sensitivity that we promised in a couple of years. And at that point, instead of running it for a few months, we're going to run it for a year or two. And Virgo should be making comparable strides in its sensitivity. So there ought to be lots of fun stuff, lots more black hole neutron star mergers. We're hoping for a mixed system, a black hole and a neutron star. We're hoping for continuous gravitational waves from like a single neutron star with a mountain on it that's rotating around, can produce a long-lived signal like thousands of years. There's going to be a stochastic background coming from lots of these things going pop very far out in the distance. When you superpose a lot of faint signals, it makes a background hiss. We ought to be able to see that by the time we get to this black curve, the design curve in 2019 thereabouts. So there should be all kinds of fun stuff coming up. And thank you for your attention.
So we have time for a few questions.
You mentioned the 2.8 number of the combined mass, and then you said that the limit for a neutron star turning into a black hole is 2 solar masses. And then
Roughly,
you said that the reason that you see a lot of these, that you get the 2.8 is because of the logistics of the two 1.4s combining. I guess the probability of that happening is much greater, but do you expect to see, I don't know exactly why that is, but do you expect to see maybe 3.9, if the limit is 2 solar masses for a neutron star going to a black hole, is it theoretically possible, maybe much less frequent?
We might, but it's tricky. Basically, the reason the 2.8 is significant is that all of the double neutron stars that we've seen have a total of 2.8. Now, we have seen neutron stars up to 2.0, but those are neutron stars with a white dwarf companion, which is very different from a neutron star. And there's a long story which, let me see, I think I can give a short version of it here, which is that in order to make the double neutron star systems, so first you have two big normal stars, right? And they live fast and die young. And the more massive one dies first. It goes through a supernova explosion, and it has to be in the right mass range to make a neutron star. And there's actually a timer there, right? So that you can actually work out as a function of mass how long they'll live before they blow. So this one blows, and then there's a random element, which is when it blows, the neutron star typically gets kicked. And so it gets punted off in a certain direction, and it can easily get punted off fast enough that it disrupts the orbit completely. You no longer have a binary. So you have to have that not happen. And then then you get into this phase. So in order for that not to happen, they have to be fairly close. And then typically what happens is the first neutron star starts accreting material from a second neutron star. So if it was born light, it starts getting a bit heavier, or from the second star before it becomes a neutron star. Then there's a timer there. There's a certain amount of accretion that happens, and then the second one blows, it makes a neutron star. And again, there's a kick issue that you can't disrupt the binary. So there's a lot of selection effects here. There's a small fraction of things that are formed, big stars that are formed in pairs. There's a small fraction of them that will make double neutron stars. And the fact that they all have almost exactly 2.8 solar masses total, almost evenly distributed, strongly suggests that there's something going on, with the timer and the accretion from one on into the other. And like I said, there's a much more complicated dynamical story behind that, but that looks like roughly the idea. And with white dwarfs, the stars that we've seen that are 2 solar masses, a white dwarf will last a lot longer, so it can dump more on its companion neutron star and get it up to 2 solar masses, whereas the double neutron stars seem to only have time to get to 1.4.
So I've got a question for you. With regard to elements, you're talking about the neutron stars being able to form gold and platinum and so on and so forth in their sort of destruction. Super heavy elements, can we get to 126 from?
So yeah, you should be able to have some super heavy stuff involved, but then it depends, is that really stable? Which, we don't know, and if it is stable, then you could form a little bit of it. But if it's unstable, then it forms and goes away.
The odds of it getting back here are relatively small, I guess.
Sorry?
The odds of that super heavy element, 126 should be the next stable isotope, I think.
Or the closest thing is
Right.
the next magic number. Yeah, it'd be again, we don't know if it's actually stable or not, and if it's unstable. So certainly there's less of the more massive ones than there are of the less massive ones like gold and platinum.
Does that mean that the universe will start, as a ratio of other elements, start being lower in heavy elements than lighter ones? I don't know.
Or higher.
I
That's
mean,
the other way.
higher.
Yeah.
Higher the other way, yeah.
Yeah, the chemical composition of the universe does change as a function of time. So yeah, indeed, in the beginning, it was roughly hydrogen, and then in the cooling aftermath of the Big Bang, you can work out how long it would take to form helium, and the first few elements formed shortly after the Big Bang: lithium, beryllium. I think it goes up to about boron, and you can work out from from an explosion how much should form, and you get roughly the right numbers, the numbers that are observed. But then there weren't any of the heavier elements, and so everything heavier than the first few got made in stars. So like all the carbon and hydrogen and oxygen and so on that makes up the majority of our bodies, that was made in the centers of stars. That's the light elements that can form down in the center. And the sun, I forget exactly how far the sun's going to go eventually, but it'll be something like oxygen or silicon. But then indeed, the time scale for these things for double neutron stars to form and spiral together is significantly longer than the lifetimes of the first stars. So indeed, it took a while longer for these heavier elements beyond iron, gold and platinum and so on, to start forming in the universe. And yeah, there is more and more of it over time. And you can actually see, it's not just that the average number changes over time. You can actually see areas in galaxies, like areas that have had a lot of activity, a lot of star formation and dying and explosions enriching the environment. Like that happens typically in the plane of a spiral galaxy, and then you'll see stuff in the central bulge, and then these globular clusters out that are very astronomers they're deprived of these heavy elements. Astronomers call them metal poor stars, because astronomers call anything heavier than helium a metal. So there's hydrogen, helium, and metals as far as they're concerned. Yeah.
You mentioned the tides, and you talked about how that influences the moon's distance from the Earth.
Yeah.
I would assume there are other things that lend to that equation that increase that, or is it?
You mean other things responsible
Yeah,
for the
I mean,
moon
like, so
spiraling
just
out?
even, yeah, just even the orbit itself, or is it just the disruption of
It's
that orbit? that's
it's basically
causing
tidal.
So it is entirely, or mostly, just that causes that to continue to go outward, as opposed to, it's not the orbit.
Well,
anything
there's
related to the orbit.
tidal stuff, and there's interactions with the fact that it's, you know, in the case of the Earth and the Moon, there's a long time of flexing the rocks and, you know, losing a bit of energy that way. Yeah, but if there were no tides, if the Earth and Moon were just point particles, then the orbit would just be a circle. Now, perturbation, you know, there are perturbations from the, you know, Jupiter and so on, but those aren't what's doing it. It's basically tidal, and that's also responsible for locking the Moon with one face towards the Earth.
Thank you.
Yeah, and I'm from engineering, and I'm doing engineering, so I'm thinking about how you can apply, like, do you have any application for this funding? Like for the black holes, where you...
Application, well, it depends what you think. I mean, one way of saying it is, like, the first application of LIGO came long before LIGO existed. So in the late 1970s, when people started, in the early 70s, people tossed around the idea of building these interferometers at giant scales and looking for really tiny signals. There was a guy named Reaver who died before he could get the Nobel, just a little bit too early, unfortunately. But he, you know, we were always saying he was going to be the third one, and basically there's something called pound-Reaver locking, which he came up with in the late 1970s, which is one of these games you play with putting extra mirrors on the interferometer to recycle some bits of the signal and so on. And like this thing called pound-Reaver locking is now standard in any industry where you want to have really high precision measurements. And so you could argue that was like 1978 or 1979 was LIGO's first spin-off. There's been other technological things. There's also sort of algorithmic things, like some of the tricks we use to look for signals are really sophisticated. Like I was shocked back in the 1990s when I was a grad student. I went to this meeting. There was a LIGO Virgo meeting back then, which had a bunch of people coming from the Thomson Marconi sonar company, which makes the sonars and the software for all the nuclear submarine fleets of the NATO members, all of the NATO members essentially. And I was kind of surprised by how much they told us, but I was also surprised that, like, I was talking about my first project at grad school, which is a mathematically sophisticated way of searching the parameter space, matched filtering for, you know, the signal for one pair of masses, M1 and M2, looks very different from the signal for another pair of masses. And if you filter with the wrong one, you lose all your signal to noise ratio. You need to put a bunch of them spaced around in the right way that you don't blow your computing budget, because each one costs. You know, you can't make them all infinite. You can't infinitely densely populate this parameter space, but you can't make it too far apart or you lose signal to noise ratio. And I had come up with this very sophisticated mathematical technique for doing that. And then, you know, when those guys gave their talk on how they did it, they were like, yeah, we just blindly, we don't do anything like that. We just have $300 million worth of computers for each submarine and made it to death with money, essentially. So we were actually, at least at the time, doing things a bit more sophisticated than what they were doing, just because we had to. Let's see, you had a question?
Yeah, I have a general question. So I'm assuming that there can be multiple collisions at the same time at different locations in the space. So how do you confirm that the two detectors detected the same event?
Well, you know, like that first one, you know, we saw the same signal shifted by 7 milliseconds between the two detectors, right? And then, you know, the rate of signals that we've been seeing so far, at least, is like 1 per few months. So, you know, if we started seeing them within 7 milliseconds of each other, like if we extended our reach, got our sensitivity to the point where we got our rate of signals up to the level of, you know, faster than 1 per 10 milliseconds, then they would start blurring together. And that's actually roughly what goes on with that stochastic background I was talking about. at that point, you just see them all, lots of faint signals all superposed as a sort of a background hum or hiss. But yeah, with a 10 millisecond window and 3 months between events, I mean, well, actually, even those last two, it was a 3-day, that 10 milliseconds was, plenty to discriminate.
Okay.
So one more question. Gravitons, I mean, that was sort of something that, was talked about 30, 40, 50 years ago.
Yeah, so, yeah, there should be, at least in the weak field limit, you talk about excitations of the gravitational field, it should be like all other fields, there should be some particle more or less associated with carrying it. The trouble is that, like when you work out the number of gravitons, like with quantum mechanics, you're seeing the difference between 1 and 2 particles, 2 and 3, 3 and 4, and even if you have a harmonic oscillator, you're seeing the difference between levels 3 and 4. That's fine because that's got like a 30% effect. But you're not going to see the difference between 10 to the 24 and 10 to the 24 plus or minus 1. And when you work out the numbers of gravitons, because gravity is such a weak force, the number of gravitons that had to be involved in these events was like 10 to the 50 or something ridiculous. So you're never going to see it tick up or down by 1 with this type of experiment.
Any other questions?
So you said the gravitational waves are formed when you have two black holes colliding, right?
Well, that's one source of them. Yeah.
So what's the exact source of the gravitational waves? Because isn't there a possibility that the gravitational waves get absorbed by the black hole itself?
The black holes do absorb a tiny amount, and that has a very small effect on the chirp rate, but it is tiny. And the reason is simply this, that the wavelength of the gravitational waves, it's like with diffraction limiting, right? That if you look for something with a given wavelength, the trouble is, you can't see atoms because the wavelength of the light is on the order of 10 to the minus 6 meters, and the scale of the atom is 10 to the minus 10 meters. So something that's less than a wavelength, the wave basically doesn't interact with it as a wave field at all. And the black holes, let's see, for that first event, so if you have these 30 solar mass black holes, you're looking on the order of 100 kilometer short-shield radius, and then the wavelength is thousands of kilometers. So there's a very tiny fraction of it that goes into the hole, but most of the waves just diffract around them because they're just too big.
All right. Well, let's thank Dr. Owen again for a wonderful talk.